All right, we have been working in Chapter 9 here, talking about significance testing, hypothesis testing. We came off of the last section where we were designing significance tests revolving around population proportions, and now we're going to shift to making significance tests regarding a population mean. Much of this process is going to be similar, although when we do talk about means, there is an element that is quite different than proportions, and I think we had discussed this with confidence intervals. We use the acronym ZAP-TAX as kind of a reminder that when we're dealing with proportions, we are exclusively using z-scores, but typically when we are dealing with means, we are using t-scores, okay? And the difference is essentially this. If you know the population standard deviation, which is generally a very, very rare thing to know, that is the only time regarding means where you would ever use a z-score. Therefore, it would be called a one-sample z-test. Traditionally, we do not know the population standard deviation. Therefore, we use t-scores, and that'll generally be what we will be using is a one-sample t-test for a mean. Okay, and when we do not know that population standard deviation, we are left to substitute the sample standard deviation is, and that's what the shift is for why it then becomes a t-test instead of a z-test. Okay, just going to run through these conditions, which at this point should feel quite familiar with you. Keep in mind these are regarding means. So it's that piece that the data has to come from a random sample, the independence piece, which is the 10% condition, and then do note that the normality check is completely different for sample means than it is for sample proportions. We've also been through this list. I've got it listed in the order where it's the easiest to confirm normality down to what would be the more challenging. Okay, and essentially, if your population is normal, then we know we can confirm normality right off the bat. We can do the central limit theorem if our sample size is greater than or equal to 30. And then finally, if we cannot do either of those first two things, we would then take the data set of our sample and we would make a graph. Typically, a box and whisker plot is an excellent graph to make. We would want to examine it, make sure there was not any extreme skewness. There can be some mild skewness, no extreme skewness or no outliers. Okay. If we feel like there is no extreme skewness or outliers, we can go ahead and proceed and move forward with doing the t-test, but we should never use the t-test if there is outliers or any extreme skewness. Okay. All right, so what we have underneath here is, first of all, looking at the rare scenario where the population standard deviation would actually be known. Okay, if it were known, we would be doing a one-sample z-test. Okay, just as a point of reference here, your test statistic, okay, your test statistic, there is a formula for this on the formula sheet, but it's written extremely generically. Okay, how it reads on the formula sheet is that your test statistic is found by taking your statistic, in this case that would be our x bar, our sample mean, minus your parameter, which would be the hypothesized value for the mean, and then you would divide that by the standard error, which in other words is the standard deviation of the statistic. Okay, I write it like this generically so that you can see how we're getting these values to be substituted where you're seeing them plugged in here. The statistic would be the x bar. The parameter, and you'll notice it has a mu with a little sub-zero there. That's because it would be the hypothesized, like the null hypothesis value from your null hypothesis, and the denominator is the standard error of your statistic, which is found by taking the population standard deviation divided by the square root of the sample size. Okay. Now, keep in mind, this is if we know the population standard deviation, we can go ahead and use this formula that would actually result in a z-score. Therefore, this would be considered a one-sample z-test. Okay. In all actuality, typically, we do not know that population standard deviation, and so the changes that would be made in that formula up above is now our statistic, still x bar, the parameter, still the hypothesized value for mu, from the null hypothesis. But here's where the change is. Instead of the population standard deviation divided by the square root of the sample size, you can see now we're substituting the standard deviation of the sample in here, okay? And that results in this now representing a t-score rather than a z-score. Okay, and I think we had been through some elements of that when we discussed t-scores with confidence intervals as well. Anytime you run a t-test, it's very important. There are a couple things that you must report on your paper on the AP test. You have to report the test statistic, which will be the value of your t-score, and you must report the degrees of freedom. Okay, remember, degrees of freedom is simply your sample size minus 1. Okay, your sample size minus 1, and the test statistic is found by that formula there. Okay, so we have some different options, just like we did with significance tests for proportions. If our alternative hypothesis is a greater than, then we're shading to the right. We would have the p-value represents that area. If it's less than, we're shading to the left, and it would be a two-tailed test if it is a does not equal to. Okay. All right, so let's go ahead and shift here to the next page where we see that mnemonic device, kind of an acronym here, that we also used when we were talking about the steps for significance tests involving proportions. Okay, these are all the same here. We state the parameter, we state the hypothesis, we list our assumptions, which are essentially our conditions, the name of the test, which for us is most likely going to be a one sample t test. Okay, only be a z test if we know that population standard deviation. The test statistic, instead of being a z-score, would be a t-score. And then to get the p-value, again, I'm just going to scroll back here. Remember, the p-value represents that area under the curve. Okay. Well, if we're dealing with z-scores, we would get those areas by doing normal CDF. Okay, something we learned back in chapter 2. Okay, but if these are t-scores, instead of using normal CDF, we're going to use the feature on the calculator t-CDF. Okay, it's going to want 3 inputs. Okay, it's going to want 3 inputs there. Essentially, t-CDF, by the way, is found in the exact same menu that normal CDF is found. It's just a couple options below. On my calculator, it's option number 6. But you would put the lower bound, you would put the upper bound, and then your third input would be the degrees of freedom. Okay, we end with making a decision, okay, whether we're going to reject or fail to reject the null hypothesis here, and then we state our conclusion in context. Let's take a look at an example here. Here, this is talking about the ABC company. It says they claim to have developed a new AAA battery that lasts longer than its regular AAA batteries. Now, based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use. Okay, so the regular batteries lasting 30 hours on average. A simple random sample of 15 new batteries lasted an average of 33.9 hours. Now, this is the information from a sample of 15 batteries. So that is representing X bar. And the standard deviation of that sample is 9.8 hours. So I'm going to label that S sub X. Okay. The question is, do these data give convincing evidence that the new batteries last longer on average? Okay. Now, when you see that phrase, convincing evidence, that is generally an indication that they are wanting you to run a significance test. So the end of a significance test is when we conclude whether we have convincing evidence in favor of the alternative hypothesis or whether we do not have convincing evidence. Okay, so we're going to begin just kind of working through our PHANTOMS acronym here. We'll start, the P represents us defining the parameter that we are running our test about. Okay, so it's going to be mu, which is the true population mean lifespan of the new AAA batteries. Okay, this is what our test is about. The H stands for us drafting our two hypotheses. The null hypothesis, which we've learned is always a statement of equality, and then the alternative, which either is a does not equal to or an inequality symbol. Okay. Now, if we look back through the problem, it mentions that the typical regular batteries are lasting 30 hours. So I'm going to go ahead and put 30 here for our equal. But we're wanting to know if these new batteries are lasting longer than the 30. So I want to choose a greater than symbol right there. Okay, the other piece that we always want to include in this H step here, you'll notice it mentions the hypotheses, and we want to state the significance level, okay, the alpha level. Now on this particular problem, they did not define a significance level for us, so we're going to use the default alpha level 0.05. Okay, the A for our acronym stands for the assumptions or the conditions. I filled these out for you here already. I'm just going to talk through them briefly here. Random, it did mention that these 15 batteries, it said an SRS, a simple random sample. Okay, so we know that that was taken. Okay, in terms of normality, it did not mention that the shape of the population mean lifespan of batteries was normal. Okay, so we can't cite that. If you look at what the sample size is, it's not meeting the central limit theorem because there's only 15 batteries in this sample size. And so we're left to determine the normality based on whether the shape of our sample data shows no extreme skewness or no outliers. Now, on this particular problem, they didn't give us what the lifespans were of each of the 15 batteries they tested in their sample, but we're assuming that someone had access to it, and that's how they were able to go ahead and construct this box and whisker plot that you're seeing right here. Okay, you always need to show the graph on your paper, and then you need to make a statement essentially saying that there's no extreme skewness or outliers. It mentions here that it shows a slight right skewness because the right whisker is a little longer, but there are no outliers. That means it's okay for us to move forward with this t-test. Okay, and then the last condition is that independence condition. As we know, the 10% condition, 10 times our sample size comes out to be 150. We need to make sure that we're feeling that it's reasonable, that 150 is less than or equal to all of the new batteries that they would have, and obviously that feels very reasonable here. Okay, so that meets the assumption condition. Okay, now we need to name the test. So the name of the test is going to be a one sample t-test. You should say for what? For means. Okay, one sample t-test for means. Okay, now for the t, this is where we are showing our substitution for how we're getting our t-score. Okay, remember the generic formula on the formula sheet says take your statistic and subtract the parameter from it. Now, the statistic is the X bar value. So we would take the 33.9. We would want to subtract from that mu sub 0, which is what we're hypothesizing in our null hypothesis that would be for the population mean. Okay, and then we divide that by the standard deviation of our sample. That's the 9.8. divided by the square root of the sample size, that's 15. Okay. If we type that into the calculator, we get a t-score to be 1.54. Okay. So essentially, you can see that right here in this graphic. Okay. It's always a great idea to draw a kind of a normal or a t-curve here. Always put 0 down the middle. We're going to show where our t-score is located. You'll notice I shaded to the right, and the reason I did that is because the sign in our alternative hypothesis was a greater than symbol, and so now the O stands for obtaining the p-value. That's that area there that I have shaded in the graph. Okay, now remember, this is not z-scores, it's t-scores. So if I want to get the t-score, I'm going to need to use the option t-CDF on my calculator. I'm going to need to label lower bound, upper bound, degrees of freedom. Okay, those calculator inputs always need to be labeled. 1.54 would be the lower or left bound. We'll go to 10,000 for the upper, and the degrees of freedom would be 14. Okay, I'm getting that because my sample size all the way back up here was 15 batteries. Degrees of freedom is always one less than that. So me labeling this as degrees of freedom counts as me reporting what the degrees of freedom actually is here. Okay, I'm going to type that into the calculator. You're pressing second VARS button, which is the distribution feature, and I think you should see the TCDF command there. This comes out to 0.0728. Okay, all right, so I'm ready to make my decision then. I'm going to compare the p-value of 0.0728 that is greater than the alpha level of 0.05. So when it's greater, we fail to reject the null hypothesis. Okay, now our statement of conclusion here. That means that we do not have convincing evidence. Now remember, what you say after this is we do not have convincing evidence that, and you want to come back up and you want to say in words what the alternative hypothesis is stating. That the true population mean lifespan of the new AAA batteries is greater than 30 hours. Okay, that is greater than 30 hours. You could say lasts longer than 30 hours. That would be fine. Okay. All right, let's go ahead. We're going to try one more significance test here. Okay, and in this example, you're given the whole body of data from the sample instead of just being given what the X bar and the sample standard deviation is. Here we have Abby and Raquel, and they like to eat sub sandwiches, but they notice that the lengths of the 6-inch sub sandwiches that they get at their favorite restaurant, it either seemed like they were shorter or they were longer than advertised. Okay, so notice there on either side, they just weren't really at that 6-inch mark. To investigate, they randomly selected 24 different times during the next month, and they ordered a 6-inch sub. And here are the actual lengths of each of those 24 sandwiches in inches. Okay, you'll notice it mentions here that they selected randomly 24 different times to order these subs. Okay, there's that phrase we're looking for. Do the data provide convincing evidence at an alpha level of 0.10 that these sandwiches at this restaurant are actually different than advertised? Not longer than advertised, not shorter than advertised, but different than advertised on average. Okay, and we'll come back and do part B here in just a moment. Okay, for part A, we're going to need to run through a significance test. Okay, so we're going to start by defining our parameter. This would be the true population mean length of 6-inch subs at their favorite restaurant. Okay, our null hypothesis is that the mean length is 6 inches, and here's where we're not going to choose greater than, we're not going to choose less than, because it says that they're different. We're going to choose that it's not 6 inches. We're going to put a not equal to. Okay, this is also the step where we say our alpha level. Okay, and then we're going to run through our assumptions, our conditions here. Okay, so in terms of meeting that random condition, we just want to mention, we look through the problem, we can see they did 24 random visits to the restaurant. Okay, I'm just going to make a note of that. Okay, 10% condition, I'm going to take 10 times, they have 24 subs here, that's going to total 240. Feels like 240 would definitely be less than or equal to all the 6-inch subs made for that month. I'm sure they make much more than that. Okay. And then our third condition this would be for normality, okay, to show that the shape is normal here. All right, well, it doesn't mention that the population distribution is normal. I'm looking at my sample size, that's not 30 or greater, so what we would have to do, I'm just going to talk you through this because I know that we've made box plots before on the calculator. You would take all of this data and you would have to put all of the data, okay, put all the data in L1. Okay. After you have that in L1, you would want to go to second stat plot. You'd want to turn on your box and whisker plot, and you would simply record how that box and whisker plot looks on your paper. Okay. Now, I don't have that pulled up at this moment, but I believe when you have it pulled up there doesn't show any signs of extreme skewness or outliers. So technically we would need to just draw a rough sketch of that, but then we also want to make a statement, no extreme skewness or outliers. Okay, so I can say therefore, which is what those three triangles mean, therefore it's approximately normal. So I've kind of met that condition there. Okay. Now we're going to want that data still in L1 to help us with something here later, but there we've checked off all of our conditions. So now we're going to name our test. Our test is a one sample t-test for means. Okay, and now it's time to calculate what that t-score is. Now remember, the t-score is taking the statistic, which would be the average of our sample. I need X bar. I need to average all 24 of these sublengths. Now, if we already have the data in L1, you can just, on your calculator, you can just press the stat button. Okay, you're going to press the stat button. You're going to bump over to the calculate menu, and you're going to pick option 1 that's called one variable stats. This is where we would always go if we were wanting the 5-number summary, or we wanted the mean or the standard deviation. Okay, I need the X bar. I need the mean for this. So you're going to press enter. It's going to give you a bunch of data for that information in L1, namely the mean length of the subs in that sample is 5.68 inches. The other thing you're going to want to write down is what the sample standard deviation is, 0.66, okay, because that is going to go in this spot right here. Okay. All right, what goes over here is the hypothesized value for mu, which is 6, and all the way under here is the square root of our sample size. I believe there were 24 subs. Okay, we type that in. We end up getting the t-score to be negative 2.38. Okay. So if I were to draw a rough sketch here, I'm putting negative 2.38 over here, and I'm putting positive 2.38 there, so that this is a two-tailed test, so we're shading each end of that. Okay. All right, now for my shaded area, I'm going to do T CDF. Okay, I'm going to focus right now on just this shaded area on the left. Lower bound, upper bound, degrees of freedom. Okay, need those labels underneath. Degrees of freedom, remember that's n minus 1, that's 23. Okay, at first it comes out 0.0130, but keep in mind that was only one of the shaded areas. So if I'm really wanting to report the p-value, I need to take that shaded area, 0.0130, and I need to multiply it by 2. So my actual p-value is 0.0260. Okay, I'm going to go ahead and make my decision then. I'm going to compare, since the p-value of 0.0260 is less than the alpha level of 0.10, we are going to reject the null hypothesis. Okay, so our conclusion, we have convincing evidence that, okay, remember what comes after the word that here is going to be a description of our alternative hypothesis, but writing that out in words, okay? And if you're ever not sure what the mu symbol is, just look back up at this first step. This is what we're going to write for what the mu symbol is representing here. So we're going to say that the true population mean length of 6-inch subs is, I'm just going to say, is different than 6 inches. Okay, or you could say is not equal to 6 inches. That would be fine as well. Okay, to close up this video here, we're just going to take one look at just an example. This is not a significance test here on the next page, but this is just asking us to kind of compare, I guess, the strength of evidence against the null hypothesis for each of these different scenarios. And so here's what we're looking at. It says, suppose that you run a hypothesis test to see if the true population mean length of 3 new species of grasshoppers is significantly less than 0.54 grams. Okay, so this is our alternative hypothesis. The null is that it equals 0.54 grams. It says you take a random sample of 35 of each of the 3 new species of grasshoppers, and you run 3 different one-sided significance tests, and here's our alpha level, 0.05. Okay, and then our results are this. Species A, that's our p-value. Here's our p-value for species B, and then for species C. Okay. We want to know what would be the conclusion that we would be drawing for each of these. Okay, well, for species A, we would be saying since the p-value of 0.051 is greater than the alpha level of 0.05, we fail to reject the null hypothesis. Okay, now we should draft our conclusion and say we do not have convincing evidence that the true mean weight of grasshoppers is less than 0.54. Okay, I'm just going to pass over that here because we've done this so much here. Okay, I'm really just wanting to compare the strength of the evidence. Okay, so for species B, we would say, okay, now since the p-value is 0.049 and that's less than the alpha level of 0.05, well then here we would actually reject the null hypothesis. Okay, and we would draw our conclusion that we have convincing evidence that, and we would finish that up. Okay, but you notice how the strength of each of these is not super strong. Like this was just really close. It was on one side of 0.05. This was on the other side of 0.05. If you look at species C, you can really see how the strength of this result is, we can be much more confident in our conclusion. That is significantly lower than 0.05. So when we are rejecting the null hypothesis for species C, we definitely can be way more confident in that conclusion versus these other two that are just right on the other side of where the 0.05 mark is. Okay, that is a good place for us to stop. There are a few problems right here that you can go ahead and try for homework.